nice mics, and the audio is going to be really good. Ah, yes, my pointer. It points at things. Okay, how we doing? We have 1 minute.
You want to wait 60 seconds?
I think everyone's here. Yeah.
Icebreaker.
Good morning, guys. My name is Maple. Welcome to Orchard Park Secondary School, home of FRC 2056. If you have any questions throughout the day, feel free to ask me. I'd like to introduce our presenters, Eric and Tyler, and we'll be presenting 2056 Ways to Code.
Welcome. Welcome to 2056 Ways to Code. Eric.
Hi, I'm Eric. I was on the team from 2018 to 2020 as a student, as the lead software mentor or student, lead software mentor from 2021 to present, and I'm currently a full stack engineer at the Go Beyond Group.
And my name's Tyler Holtzman. I've been building robots for a long time. In my professional life, I'm a senior design engineer for Lakeside Custom Machinery. We build like custom automation for the food industry. So it's like a lot like FRC, except like our game piece is like a bag of potatoes or like a raw chicken breast. So sometimes it's kind of gross and sometimes it's kind of cool. I'm actually doing a job right now that's conveying the tubes that grease go into. So they're like these white PVC tubes about yay long, about yay big. And I got like a bunch of tubes on my desk. And I'm like, this feels oddly familiar for some reason. So they're like super flimsy though. So anyways, moving on. Is this me or you?
Yeah. So we have a couple things we're going to go over today, as you can see here. We're going to talk briefly about the programming language we use, how we plan our software, the subsystems that we have, how we do robot controls. We're going to talk about how we did vision, especially last year. And also we're going to talk about our autonomous philosophy.
So programming languages. There's a bunch of different programming languages that teams can use. And there's no really best one. Teams should all make an informed decision for themselves which programming language they want to use. There's C++, Java, Python, a few other obscure ones. But you should just use the language that you know the best. For 99.9% of teams, there is no performance difference between any of these languages. So you should just use the one that your team mentors and your team students have the most knowledge in, which for the vast majority of teams will be Java. We use C++ because we've been using C++ forever, and I'm too old to learn something new. So we use C++. There's really no reason other than we've had a lot of experience with it. And like syntactically, the languages are very similar. There's just a dot instead of an arrow and things like that. So it doesn't really matter which language you choose. Pick the one that you know best and stick with it. Finite state machines. So a lot of teams use command-based programming for their robots, and that works really great. We don't. We basically build finite state machines for the control of all of the subsystems on our robot. And fundamentally, what a finite state machine is a method of controlling something that has unique states that it could be in and how to get from state to state. So at a very high level, you can represent it as a flowchart, kind of like this. Or maybe a better example is something like this intake. This intake, from a programming side, it really only has, like the position of this intake has two states, which is physically down and physically up. So in the up state, we command the motor for the rotation to the up position. In the down state, we command the motor to the down position. And then in between those states, we have an action that happens that makes the finite state machine switch from one state to another state. We call those transitions. So a transition could be a lot of things. It could be the driver pushes a button on their joystick, and that makes the state machine switch to the other state, which then commands the intake up. Or it could be a timer that expires. So we're going to put the intake down, and after half a second, we're going to command it back up. Or it could be this sensor that shoots across here, we're going to put the intake down button. It's going to put it down, run the rollers until we see this beam brake get broken, and then command the intake up. So with a finite state machine, your transitions could be any logical condition that you can think of: timer, sensor, button press, something that evaluates the true or false, that makes your state machine switch from one to another. And you can build very, very complex functionality like this within your programs. Yes.
So Ty did a great job explaining and kind of showing it off with the robot. And you can see, maybe, this is a state machine that we drew up for last year's robot. So you can kind of see here is a great example of maybe something you would do before actually programming, where you have, again, your intake is off, and then maybe you hit the intake reverse button, and it goes into this reverse state. Can you even see that? No, you can't see that. Okay, well.
Oh, you can kind of see it. There's little arrows here. So these arrows are the transitions. These are the things that make it switch from one state to another. And then these are the actual states where stuff happens. So in the intake on state, we're running the intake rollers in to pick stuff up. The intake reverse state is we're spitting the intake back out in order to purge something because we accidentally picked up 2 notes. And you'll notice the transition for this is the button is pressed, and the transition to go back is the button is no longer pressed. So that's how we get in and out of this state. But some other states, we press the button, and you actually have to press a different button to come back, or the sensor is made and we move on to this other state. So you can build up really complex functionality like this. And when we sit down to start programming our robot, like at the end of week 1, after we know roughly what it's going to look like and what motors are going to go where and what things we're going to have moving, we draw out flowcharts exactly like this before we start programming anything, and then we build our software based on these. And this gives us a good starting point. It's not the be-all, end-all, and we find lots of things that we have to tweak and work in kind of crappy workarounds along the way. But with this general structure, we can kind of hack in goofy things that we need to do to achieve the functionality that we want. Yes?
Can you be in multiple states at one time?
No. You're only ever in one state at a time.
Per
And
function.
Per
per
subsystem.
subsystem. So we build a state machine for the intake, and a subsystem may actually have multiple actuators.
Mhm.
Like the intake may actually consist of the rollers that drive that, plus the rollers that feed the shooter, for example. All of the examples we have in this programming session are for this robot, because this robot was really simple, and this robot was a great example of what to build. This robot was really good, but it was way more complicated than we really wanted it to be. And the control structure behind it started off reasonably simple, but just like snowballed out of control. So we're not going to go into a ton of examples. Like the intake state machine for this consisted of these rollers, this pivot, those rollers, that sensor, that sensor, that sensor, and it had to talk to the elevator. So like there was a lot going on in that one, and it had like 20 different states by the end of it. So this one was a little bit messy. But because we started with this functionality, it enabled us to do the crazy stuff that we had to do for that one. In general, build your robot simple. This was a more complicated robot than we really wanted to build. Questions? Okay.
We have a quick snippet of code. For those more interested in the actual code part that I guess you can't see because of the light, we use switch cases where each state is a value in the switch case. And there's a snippet of code that you can see whenever we upload these.
So if you don't know what a switch case is, it's kind of like an if-else statement, except only one of the things ever evaluates to true. So you've got one variable that goes in your switch, and then you have a whole whack of different cases that your switch could evaluate to one of those different things. And then at the bottom of that, we have if the transitions you want you can achieve from any state, you put the transitions at the end outside of the switch case. If you have transitions that you only want to be able to happen from within a specific state, then you put those transitions within the case for that state that you're in. So you have your intake goes down, and I want to bring my intake up when that sensor is made or when the driver presses the intake up button. So the intake up button is going to be a global transition that I can go to from any state, but that sensor transition is only going to be within the intake out state, for example. I wish the lighting was better in here. I'm sorry.
Yeah.
Okay, we just glazed over state machines very quickly. Yes.
I'm just wondering in your switch statement when you start to transition between states, does that happen in each of your state? If you block, like how do you block some contradicting state, or is it like just blocking between the states?
So we build each subsystem with its own state machine, and that happens once per cycle. So we never have each of the different state machines executes sequentially. So we never really have conflicting stuff, and we try to avoid the number of state machines that have to interact with other state machines. And if we do, then we're just careful about the execution order in which we put them in, so that we don't have like one thing is commanding one thing to one state, and then the other thing is commanding it back to the other state, and then you end up like thrashing back and forth between two states. And so you can shoot yourself in the foot if you're not careful. So be careful. More questions? Yes.
How does the switch statement differ from like if you did like an if and then elf change?
It wouldn't.
It wouldn't?
When you're comparing a variable equals a state and you're just looking at one condition, it is effectively the same.
Yes.
But it's when you have multiple conditions that it's not the same.
Yeah, we generally make
But,
an enumerated type for the states, and we'll call them intake in and intake out, and intake up and intake down and intake left and intake whatever they are. But that enumerated type really just evaluates to an integer. So you could make it if state equals thing up, if state equals, but the case switch is just a little bit cleaner way of writing it. Functionally, they're exactly the same thing. Yes.
So when you have different subsystems, so for example, with the elevator and the arm, how are you actually managing the interaction between those? Are you using a handler or?
Very carefully. We generally try to make the one system inherit another and not the other way around. So for example, the intake in here, they both had a shared sensor at the end of the thing. So the intake would drive the coral all the way to the end of the little cradle there. And the elevator, if it was in the home state and that sensor was made, it knew to go down and grab that coral. But the intake state machine didn't actually talk to the elevator state machine and tell it to pick up a coral. We just had this sensor that both of them could see. And yeah, that's how it knew to do that.
Like when you're designing the robot, you're very careful as to where these transitions end. You don't need a handler, or?
I'd like to say that we think that far ahead, but we don't. We kind of just figure that out as we go. But yeah, we don't have a high level kind of handler that handles most of those things. Yes.
And how do you handle different person working on possibly on different parts of the code? Do you have one person that handles all the subsystems, or you have sub teams that communicate and work on their own piece of code?
Do I have the? So generally, when we program, we'll put like literally a big TV in here, and we have one laptop at it, and then a bunch of people that kind of sit behind, and one person will be at the computer, and we generally only work on one portion of code at a time.
Mm-hmm.
We don't have like parallel development of the intake and the elevator. It kind of just all happens serially as we're going. So that does limit us into our throughput, because everything ends up flowing through one thing, but it does avoid having conflicting things, and we're sure that we have a high level architecture that's keeping track of everything so that everything kind of follows along.
But still, it's a teamwork.
Yeah.
It's sequential.
Yes.
It generally helps as they're designing the robot. We do have some of the kids do their own like subsystem to get the very like low level basic infrastructure in the code. But then yeah, when we're actually like doing the fine tuning, it's a big group of people.
Yeah, we build the state machines like in PowerPoint
Yep.
with the states and what happens in that state, and then you can go off and write all that code and get it 90% of the way there. And then when we power the robot on, we see, oh, we're missing a transition for this weird edge case that we didn't account for, and we'll add that in and kind of figure that out kind of on the fly. Yes.
So when you said you work together with the students, right?
Yeah.
So like, is that PowerPoint piece and the code piece? Like your
All of it.
Okay, so then how many, just curious of numbers wise, how many students say would be, if you're doing it serial and you're coding something,
Yeah.
like you're ready to code it, how many would be sort of around the computer with one person coding? Like how many?
2 or 3.
2 or 3?
Yeah.
Is that your, like the sub team size, is that, or?
Generally, like some years we have kids that are really interested in programming, and some years you have less, and then some years you have one, some years you have none. So it really just depends on the students you've got and what they're interested in, and making sure that they're involved in a meaningful way and following along, and that they know what's going on, and getting them to take ownership over a piece of code is really nice. Like maybe they can write write an individual subsystem and write out the switch case beforehand, and then if they've written the whole thing out and they understand, what is supposed to be going on behind the scenes, when you power the robot on, you can realize that, oh, we're missing this one transition, and we can't, if we pick up a coral and then go to L3 and then we realize we need to go to L2, well, we can add that extra transition in to do that. And this robot, the startup of it was a lot of that. Is there were so many different combinations of things that you could do, that we went through a lot of that kind of iteration. Mark, that's why we don't have any of this robot as examples in here. Like one button on that joystick did 4 different things depending on what was happening. Like if we had a coral, if we didn't have a coral, yeah, it was complicated.
It's quite complicated. It's very kind of painful. That's okay.
Anyways, moving on.
Moving on.
More questions on state machines before we move on.
No, we have to move on.
We have to move on.
Yes, we have a lot to talk about.
Control loops. I'm going to very briefly talk about control loops. I could give a whole talk on control loops, but what we're talking about is how to make something do something that you want, how to make an arm go to exactly here, how to make a drivetrain drive to exactly here. We generally use the CTRE control loops because, well, they're better than anything that we could write ourselves. So the CTRE control loops, they run on the motor controller themselves. And they're like 1,000 times per second. It is calculating how far the motor is from where it wants to be, or what the delta in velocity is from what you're commanding it to. And it's adjusting the motor power to make it do the thing that you want it to do. So the CTRE control loops are awesome. You can do pretty much everything with an FRC robot now with like motion magic position, velocity control, and like open loop position or open loop power to a motor. So this whole robot was just motion magic position for the elevator, the intake, and the wrist, and the hanger. And then the rollers, the other rollers, and the other rollers were all just motion magic velocity. And the drivetrain is velocity control for the wheels and PID position for the steering. We use position for the steering, not motion magic position. There's not a huge difference. It just doesn't have the XL ramp when you're commanding the wheels to a specific heading, so it gets there a little bit faster. I don't know that it actually makes any difference, but it works for us, and we just don't have any reason to explore other things. Questions on that? I know I glossed over that really quickly. Yes?
You mentioned motion magic velocity on the rollers.
I'm sorry. Velocity control. It's velocity voltage on the rollers. Yeah. There is a motion magic velocity now that actually does XL decel ramping, but it's not necessary. And we found that when we tried it, the XL ramp was too slow, that we couldn't stop the coral fast enough when we were conveying it into the cradle. The funny story, the first time we powered that robot on, before we had everything dialed in, we picked up a coral and it like flung through the aligner and busted the back right out of the coral holder. Like it literally ripped the whole back of it off and fired the coral out the back of the robot. And I'm like, oh, I guess we gotta slow that down a little bit. So yeah, coral is very violent, and that thing is way too fast. More questions? Yes.
You were saying that on the you weren't using much magic on the drive-based turning.
Yes.
You said. So if you were doing any sort of like drive to the post or like going to a specific spot, were you using any sort of profile control there, or was it strictly like a PID controller type thing to get to that?
So for autonomous driving, we have our own like basically it's a PID loop to a specific point. So we calculate the heading to the point. We know the distance from the point, and then we feed basically the distance and the heading into the field-centric robot controller that we use for driving in teleop, and it commands the robot to that specific point. And that's just a straight PID loop. It's just a straight PD loop, actually. There's no I.
Profile that also, or was it just strictly like?
No, there's a slew rate limiter that eliminates the like large step in velocity change when you suddenly command it to a new point, but it's very aggressive. It's like, I think it was 600 inches per second. So it's like 300 milliseconds for the robot to accelerate to full speed, or for the commanded velocity of the robot to reach full speed. And it's just enough to get rid of the large step change. Yeah. The way we do it is not the most ideal way by any means, but it's easy. And we've been doing it for a long time, and we just don't have a reason to change. So we just keep doing it the same way. Okay.
Next.
Whoops. Robot controls.
So we touched on this briefly when he was talking about how one controller or one button on the controller does a bunch of things. And part of the reason it does that is because our philosophy for robot controls is to have one person doing all of the things. So we try not to have, and you've seen that the last 2 years, we don't have someone driving the drive base and someone else, putting the arm up and actually scoring. It's all one person. And we do this because, as it says, talking is slow. If you have to talk to your operator to figure out what the next action is, this is time that is kind of just wasted, and it slows you down. So instead of doing that, we, again, have one driver, and we accomplish this a lot with driver assists. So we'll talk about it shortly, but we have a lot of vision on the robot. So when he wants to score, it's as simple as driving up to the thing, hitting a button, and then hitting a second button, and it scores. And that's it. An important thing that we have to remind Ty of is that it's not always about him, it's about our driver.
Yes.
So it doesn't matter how he likes to drive the robot, it matters how they like to drive the robot.
Yes.
And that's important. If your driver can't drive the way they want, then that's almost what's the point. And you can see here, this is last year's robot code or robot controls. I don't know how well you can actually see it, but you can see each button has its own thing that it does.
So left stick was translation, right stick was rotation. Right trigger is always like shoot or score or do the thing that gets you points. And then these face buttons are things that your robot can do when the driver also doesn't need to be rotating the robot, because their thumb has to like come off the rotation stick to press one of those buttons. So you want to make those something that's like reasonably infrequent, or something that they do when they're not also rotating. We use these Xbox PowerA Fusion controllers that actually has mappable buttons on the back, and then we map them to the D-pad values, so that it basically adds kind of 4 extra buttons that normally you wouldn't be able to use without taking your thumb off the translate stick. But then nobody uses the D-pad anyways, so it basically adds kind of 4 extra buttons. And yeah, this robot was great. Like the controls were really simple, and it was not a hard robot to drive. Questions on controls? Okay, great. Vision tracking. Yes, sorry.
How much time do you have for your drive team to practice with the robot, and when do they do that first, and so on?
That's a great question. So the question was, how much time do we have to practice? So we generally have one robot like together, powered on and functional by about the end of week 4 after kickoff. So there is a long development period after the robot is powered on before it's really like competition ready. But we generally don't start driver practice until it's competition ready. Like the state machine is built, the automatic scoring actions are in place. We don't really start practicing properly until like the robot's in a competition ready state. So powered on and moving at the end of week 4, and then kind of competition ready week 5.5, week 6. And then there's generally 2 to 3 weeks before we compete where the robot is in a competition ready state where we're actively practicing and making improvements before our first event.
And you do this so that your driver isn't practicing with a robot that's like not ready. So if maybe there's a little, quirk or weird movement that it does, and he practices and he learns how to practice around that, then all of a sudden we get rid of it, and maybe he has this little quirk that he doesn't need to do anymore. So
the robot needs to be competition ready on time for this philosophy to work. If your robot's not done on time, well, you've already got bigger problems. But yeah, your robot needs to be done on time, and you need to give the drivers time to practice. Ideally, a couple of weeks at least. Okay. This is what we wanted to spend the bulk of our time on today, is actually vision. And a lot of teams ask us a lot of questions about vision and how our philosophy differs from other teams and really the community in general. So we're going to talk about 2 things in general: pose estimation and game piece tracking. So when I say pose estimation, what do I mean by pose estimation? Well, it's really using computer vision to figure out where your robot is on the field, or where your robot is in relation to things that you want to do stuff at, like scoring on the reef, or picking up a coral from the human player station, or scoring an algae in the barge. You'll notice that we don't have the April tags up here on the barge. Ain't nobody got time for that. So that's really what pose estimation is. And that's obviously a valuable thing because our robot needs to be able to drive around the field accurately to score. So pose estimation is really important. So there's a couple different ways that you can do this. And there's these MegaTag 1 and MegaTag 2 are 2 kind of functionalities that are built into Limelight's canned software that spit out a position on the field relative to the April tags. So it's kind of this magic black box that tells you where your robot is. Each of these have advantages and disadvantages. And to be perfectly honest, I'm not super familiar with either of them. Some of you will probably know more about this than I do. But from my limited understanding, the MegaTag 2 takes in the gyro orientation so that you can avoid any kind of ambiguity if you're looking at a tag from this angle or looking at a tag kind of from this angle, because from the camera's point of view, it's not always obvious which one you're at. So if you fuse the gyro in with that calibration, with that calculation, you can eliminate one of the kind of ambiguous poses. So this one is generally better when you have one tag in view. Do you know?
Yeah, it depends on the distance you are from the tag as well.
Okay.
How frequently you can update the gyro reading. If you don't have a frequent enough update on the gyro reading to the Limelight, it's significantly worse. Like while you're driving, if you're turning too quickly while looking at tags, MegaTag 2 is actually pretty bad because it relies on the gyro reading.
Okay.
fancy.
So we actually use a different method that we call MegaTag at home. And we generally avoid the kind of 3D methods for looking at tags. And the reason that we avoid them is because they're much slower than the 2D methods for looking at tags. So the Limelight works in a couple different ways, and you can set it up however you want. But with the 2D methods, it only tells you where the tag is in the camera's field of view. It doesn't tell you where your robot is in relation to the field in Cartesian coordinates. It just tells you, here's my camera. The tag is 4 pixels to the right and 3 pixels down from center. But it does that really, really fast. Like 120 plus frames per second with the new Limelight 4. Even with the previous generation Limelight, it's still like 70 FPS or something. It's way faster than the RoboRio. So what we do is we build our own map from some value that comes back from the Limelight to other useful values that are in the real world. So this year, for example, we mapped the area of the April tag in our field of view to our linear distance away from the tag. And that's this like really nice linear relationship that when we're up really close to the tag like almost fills up the entire field of view of the camera. And when we get farther away from the tag gets smaller and smaller and smaller. And you can build a interpolating tree map just with a tape measure, laying it out on the floor from your linear distance away from the tag to the tag area. So we built this map to measure the distance. And then in the camera's field of view, we know what the angle. Well, I got this all out of order. We know what the angle of the tag is relative to the robot. And the tags, we know where they all are on the field. Like there's a big list of coordinates in the game manual that says where each tag is. So if we see a tag number 3, we know where that tag is. We know how far we are away from the tag. We know the orientation that our robot is in, and we know the orientation of the tag relative to our robot. We can build our own mega tag at home method that tells us where our robot is using only 2D methods that work smoking fast and is good enough for the autonomous driving that we're doing. So we basically just made a cheesy version of mega tag that is not as accurate, but runs way faster. And that's what we use for our driving. I say it's not as accurate. It's not as accurate everywhere. It's actually more accurate in a very, very specific spot, which is when we've got the coral right on top of the reef. And that's really where you care about your accuracy. Like if I'm driving around out here in open carpet and my vision is telling me that I'm actually here, but the robot's actually here and I got a 6-inch error, we don't care. Like you're in open carpet, you're not doing anything. You only care about the accuracy when you're going up to score the coral right on top of the peg. And at that time, the vision, the April tag fills like 80% of the view of the camera, and we have a super accurate position in that one specific spot. And it works like smoking fast. So you can just like close loop on the actual values coming back from the camera without doing any like latency compensation or any of the fancy programming stuff that is over our heads. So I know I just threw a lot of information at you. Are there any questions? Yes.
Okay, so if the performance wasn't an issue, like say the new Limelights, you could get high enough FPS on the 3D.
Yes.
Would you see any benefit to choosing that over the 2D, or would you stick to 2D even if you could get like way higher?
I would want to test it,
Okay.
but we did a little bit of testing with the new Limelight 4s after the season running MegaTag 2, and it was remarkably good. And it was still, do you remember how fast it was?
It's still 60, 70. Yeah.
Yeah, it was fast enough to just use that value. Now that's recent addition with the Limelight 4.
Mhm.
When we started last year,
Did not have a Limelight 4.
Limelight 4 wasn't out. And so we started off with Limelight 3s, and it was not fast enough. So we kind of built our whole 2D tracking approach. And then Limelight 4 came out, and we wanted to use that for game piece tracking. But we already had some Limelight 3s from last year, and they're not inexpensive. So we put those ones on for April tags, and we put the brand new one on for the game piece tracking, not realizing how much of a performance benefit the Limelight 4 would bring had we also used it there. So I think going forward, our approach will just be Limelight 4, MegaTag 2, just use that value because it's quite good now. It's good enough that you can not latency compensate and just use those values and trust them, as long as you can see a tag. And if you can't see a tag, then you just do it the old-fashioned way, which is count your wheel revolutions and dead reckon driving. More questions? There was a question at the back. Yes.
How do you construct, like, it's sounds like you're just collecting data points for the entire home.
Yes.
How do you construct like a graph? Like for
I'm glad you asked. You can't see that at all.
You want the real code?
Sure. In WPILib, there's a thing called the interpolating tree map. And the interpolating tree map is basically a lookup table from one value to another. So you give it a whole whack of data points. Say you're measuring the tag area. You give it an array of data points of the tag area and then the corresponding value that is, I'm measuring this with a tape measure, and this is how far my robot actually is away from the thing. So we park the robot right up against the April tag. The tape measure reads 0, and we say the area is currently 25. And then we back it up 6 inches. And the tape measure says 6 inches, and the tag area from the limelight says 21. And then we back it up 6 inches. And we back it up 6 inches, taking measurements all the way along, building up this lookup table. Ah, there you go. So there's the area that comes from the limelight, and that's the actual measured distance in inches. And then when you use the interpolating tree map, when you call the get function from it, you pass in a value that corresponds with this column, and it will spit out the value from this column that corresponds to it. And if it's in between, it will kind of linearly interpolate in between the two of them. So say I gave it a value of this, but it was 8 instead of 7. It would give me a number linearly in between those two. And then we can basically take that function and get the distance from the area. There's a lot of things with Limelight you can do where you can use the values like the area or the height of the tag or the TX value, or the position in the field of view this way, or the TY value, the position in the field of view this way. You can take that information and build an interpolating tree map into values that are actually useful for you, like the linear distance away from the thing. Because nobody really cares what the tag area is. You want to know, how far am I from dunking on this pole? Does that answer your question? More questions? Yes.
And then I assume because this year, like the reef was all the same distance, did you just have one set of values depending on the tag, or did you look for a specific tag?
It was one set of values.
It was one set of values. We had different offsets depending on whether we were level 2, level 3, or level 4.
It was the same.
But yeah, it was the same. It was the same distance.
So you weren't looking for specific tags in that case?
Our auto aim, you would point it in front of a tag. It would look at the tag and go, oh, it's tag number 5. I know for tag number 5, my robot orientation needs to be at 30 degrees. And I want the tag to be centered in the field of view of the camera. And because we had 2 cameras that were offset by the 2 reef poles, we could always see the whole tag when we were in position for scoring. And the tag was always dead center in the field of view of the camera when we were in the scoring position. The design of the game largely dictated the position of the cameras on that robot. And even the mechanical design of the elevator was driven by the positions of the cameras of those 2 robots, even though they're seemingly unrelated things. But like the stance of the width of the robot, the elevator, we knew the cameras needed to be roughly there in order for them to see the tag completely when you're, whatever the offset was for the reef pole. A lot of teams like put the cameras down on their swerve modules, like pointed up like this. And then the tag is like on some weird angle when they're trying to score. And then putting your cameras like in the middle of your robot so that it lines up with the thing that you care about is really beneficial. And putting a little bit of thought into that when you're designing your robots from a mechanical standpoint makes programming way easier in the end. Yes. So we've got a gyro on board the robot that's constantly measuring the orientation of the robot. And the gyros now are good enough that you can just trust that as the true value. So we know where the robot's pointed in space all the time. Yes.
I guess gyro thing. So do you set the robot specific at start to a known angle, and then you never update the gyro throughout the entire match?
Correct.
Even when you're stopped looking at the tag, you wouldn't touch the gyro, like reset the gyro angle?
Yeah, we don't reset the gyro angle at all.
Okay. And then to drive square to the reef in this model here, so are you like you know the known angle, right? To be like perpendicular to the reef or
Yep.
facing correctly, right? So you would be looking for a specific area, and then would you like drive the yaw to zero, or would you just base it off of your gyro's angle to the known angle that you want to get the robot to?
So
Is it a combo of like area plus gyro?
we kind of use a combination of things. Like we know the area, we know the distance away from the tag, we know our angular heading. So we just calculate a pose relative to where we see the tag, and then drive to that pose.
As the button is pressed at that moment, you do that calculation and then do it like a drive to that specific pose.
When the button is held, we do that calculation every single cycle, updating the desired pose of the robot. And then as it approaches that, it gets closer and closer and closer. Our distance estimation gets better and better and better until we're in position right at the thing. One kind of cheesy workaround that we do is we don't immediately snap the heading to the ideal heading for scoring at the reef pole, because if you're off to a side and you snap immediately, you may end up looking at a different tag. So we actually snap the robot heading to the average of the ideal heading plus the TX from the camera. So it kind of like, if I want to be here, it kind of like approaches it on an angle and then squares up on the way in. Yeah, it just kind of keeps you pointed at the tag that you want to be looking at. There's like a million cheesy little workarounds like that in our code, and those things are like the lifeblood of FRC, and what makes the difference between the 99th percentile and the 99.9th percentile. Okay, I just glazed over a lot of stuff.
It's just game piece tracking.
Oh yeah, so game piece tracking. Much like we do with April tags, we can use the interpolating tree map to basically go from TXTY to linear distance away from our game piece. So last year we used the Limelight 4 with the Halo accelerator. Thank you. And it's like a little GPU that you put in the Limelight 4 that enables like machine learning models to run. So Limelight has their own machine learning model that they've trained that will tell you what a coral is in the field of view. So I'm going to apologize about the brightness, but it's tracking this coral underneath the algae right there on the field with a 92% confidence that this blob of white pixels is a coral. So we used the machine learning model last year. In 2024, we used the Limelight 3G, just looking for an orange blob of pixels. We didn't use the machine learning model. We just looked for orange pixels on the field. And it turns out in an FRC arena, there are very few orange blobs of pixels that aren't notes on the field. So we just used plain old simple color tracking on a Limelight 3G. And you'll notice here that it's like 90 plus FPS. So it's smoking fast. It's way faster than the Rio. We can just use that and servo on the values coming back from the camera. So depending on what the game piece is going in future years, maybe you can use a Limelight 1 tracking color, and it's going to be just fine, or Limelight 4 with the Halo machine learning to track stuff. Now, the way that we figure out where this coral actually is the same way we do with April tags. We build an interpolating tree map from the Limelight TY value, the Limelight TY value to the linear distance away from the robot. We know where the robot is. We know that the coral is 6 feet in front of me and 3 degrees off to the right. And I can calculate the pose of where that coral is. And then I can command the robot to drive to that pose. And it's that simple. You can do this with color blob tracking a note, or you can do this with AI tracking a piece of coral. It's really just that simple. Now, where this model falls apart is if the coral is not on the ground, it's going to be higher in the field of view of the camera compared to one that is on the ground. So it will artificially read as further away than you are expecting. Why is that dangerous, you ask? Well, because when the coral drop out of the human player station, it drops from several feet up in the air. So when we were developing this robot, one of our big challenges was when we would drive back to the human player station, if the human player dropped the coral too late, the camera would see the coral up in the air, think, oh, wow, my coral's really far away. I need to drive really far, and just clock the Alliance Station wall. So yeah, that's not ideal. We ended up building like virtual bounds around the playing field so that if the robot detected a coral that was outside the playing field, it wouldn't try to go drive it. But many intakes were sacrificed before that time. So yeah. Questions on that? One thing you'll notice, or maybe not, but the game piece we're tracking here, when you're doing any of these tracking methods, 2D tracking methods in Limelight, there's a little selector box that you can pick where the crosshair that Limelight tells you in relation to the center pixel. So we have our crosshair defined way down here, like basically at the front bumper. And we have the crosshair for the game piece selected at the center bottom of the image. And the reason we did that,
You can kind of see it better here on the notes.
Yeah, with the notes, if they're in the center, it's one thing. But a note always lands like this. A note is the same which way.
Yeah.
A coral, depending on which way you're looking at it. How do we have no coral? There we go.
Oh God.
A coral, depending on which way you're looking at it, imagine you're looking at it from above, like the camera is looking down like this. A coral, if I have the crosshair in the center, is like here. But if I have it in the center this way, it's actually like out here. So we defined it at the bottom edge so that no matter which way this was oriented, the bottom edge is still the same distance linearly away from the robot. And you can choose a whole whack of different options. You can choose bottom center or top right or top center or all the way around the kind of bounding box that it defines the game piece as in the field of view. But using these little tools and the little selector boxes to get the values that you actually care about and consistent good data turning into real world numbers like the linear distance away from your robot, knowing all these little tricks is really critical to making a very simple system work very reliably and very robustly. And putting thought into where you're going to put your cameras. Like this camera is mounted way up in the air, basically as high as we can mount it in a protected position to detect this game piece, because we wanted to have a big height delta between the floor and this. If this camera was mounted down here, even when the game piece is really far away, the delta in the field of view of the camera doesn't change that much. So putting thought into where you put your cameras is just as important as all of the programming stuff that goes along with making something like this happen. There are no problems in FRC that are a programming problem or a mechanical problem or an electrical problem. Literally everything in FRC is a systems design problem made up of mechanical components and electrical components and software components, and these things all have to work together. So it's important to not get like too pigeonholed into, I'm a software guy, all I do is software, and this is the camera that I've got. Well, maybe making a mechanical change is the answer to a programming problem. Yeah, so there's our game piece. You can't see this at all. There's the like linear distance away. That's the TX value. That's how you calculate the vector from your robot to where the game piece is. One thing that's kind of important is all of our calculations for the robot are based on the robot center point. When we're picking up a game piece, the intake is actually like 20 inches in front of our robot. So we add a like extra vector that is 20 inches to account for the linear space. So the point that we calculate where this is, we actually want the robot to be 20 inches back that way relative to this so that we don't like clock the intake into the wall. Ask me how I know that. Moving on.
Auto
Okay.
modes.
Before we do auto modes, are there any more questions on vision? That was a lot. Yes.
So when you guys do coral detection, how does the actual control on the driver work?
That's a good question. In auto, we calculate a pose for the coral and we drive there. In teleop, if the driver holds down the intake button and there is a coral in the field of view, when the driver pushes the stick forward to go pick up the game piece, the robot will add in some robot-centric Y velocity proportional to the TX value coming from the camera. So that if the coral's off center and the driver is pushing the robot that way, and the robot sees that there's a coral a little bit off center, it'll actually like kind of steer the robot over towards the coral very subtly. It's not a big aggressive move, but it just adds in a little bit of robot-centric Y velocity proportional to whatever the TX value is coming from that camera. So it's very subtle. It doesn't like you hold the intake button and the robot automatically drives there. Like you still need to like drive the robot in the general direction of the coral, but it will slide side to side a little bit. How are we doing time-wise?
Developers asked, what was the value density you used for the distance interval training?
The value density.
Value
6 inches.
Was it every 6 inches?
It was last year. This year it was a lot bigger.
Yeah. The value density at any one point doesn't really matter. The more dense you make it in the areas where you really care about the values, the better. Like you could do every inch where you're in the scoring position, and then every foot when you're further away from the scoring position, and that would be just fine. But with that interpolating tree map, you don't have to do every 3 inches. You can do every 3 inches in a specific area where you really care about it, and then every 2 feet or 3 feet when you're 8, 10, 12 feet further away. More questions? Okay. Oh, sorry.
Auto modes. The way we develop auto modes is quite simple. We drive to a point and we pick up a thing, and we drive to another point and we score it. We don't use any of the fancy path planning software, and it's all custom in-house code. More specifically, when we're actually making a auto mode, the way we do it is we start simple and we work bigger. So at the beginning of a season, we have a working drive base, drive forward a foot. And then once you can do that, drive forward a foot and maybe pick up a coral. And then once you can do that, drive forward, pick up the coral, and score it. And testing as you do this, you don't want to write an entire auto mode and then run it for the first time and have it blow up. That's not a fun time. More specifically in code, for those of you curious, we use these switch cases like we do with state machines. But they don't work like the state machines. It's more of just a step-by-step list of instructions. So we have some variable that starts at 1 and then does a bunch of stuff, like maybe drives to a point. And then when we're within a foot of this point, this variable increments, and then we go to step 2. And then maybe when you have a game piece, it'll go to step 3, and so on and so forth.
Yeah, the auto modes are really just a finite state machine that happens very linearly, and stuff happens along the way. The transitions are, I'm within 3 inches of this point. The transitions are, the elevator is up in position. The transition is, the wrist has dunked the game piece on the pole. Then the next state might be, I'm driving over here and I have picked up a game piece. And then the next state might be, the game piece has reached the cradle and I have picked it up. And then the next state might be, I am in position to score over top of the pole. And that was literally how our auto modes have been built for the last 15 years.
Really forever.
So we don't use any of the commands or the auto scheduler or pretty much any of the CAN software. But the way we build it is also super simple that you can just like hard code it in a few minutes.
Yeah. That's really it there, we have to say, about auto modes. So questions?
Yes.
So when you're creating like a specific auto mode, right? Like, let's say left side reef that you're scoring on. Is it literally just that set of instructions in that file? And then
Yep.
you just call that file?
Pretty much. Yes.
But still, you make it look very simple, both the control and the auto mode. But in the last few years, you won a lot of auto prices and control loops. So what is the secret ingredient? Although it's simple, you make it be the best for this and won awards.
I genuinely don't know.
The secret really is that it is simple.
It's
Like,
simple and it's reliable, and the
Yeah.
conditions that we have that make it move on to the next things are reliable conditions that we don't get like stuck in a spot waiting for the gyro to be exactly 90.0 degrees. Generally, the tolerances that you can allow for the position of the robot driving around the field can be quite large, except when you're like going to dunk the game piece. So like when we're just driving around on the way to something in autonomous, the allowable tolerance around the point that we want to get to before we move on to the next one might be like 2 feet. And that's okay, because it's just an intermediate point on the way to another point. When we go to score, the elevator has to be in position within like 1 or 2 turns of the motor, and the elbow has to be in position, and the robot has to be within the commanded point of, I think, about 1.5 inches radially around where we think we want to be before it dunks. But just carefully choosing the right tolerances to accomplish what you want to accomplish, and running the auto modes like 6,000 times.
Yeah.
That's really, we leave a lot of time for auto mode development, and it represents a lot of our development in the back half of the season. This year was kind of an anomaly where we went to our first event with an auto mode that was like 95% of the way there. And then the majority of our development between our first event and our second event was purely mechanical. And we put almost no time into autonomous development between our first and our second event. But that was just because we realized that we had to hang. So yeah, you got to put a lot of time into it. You got to build your robot quick. You got to know when to use a hammer and when to use a computer to solve a problem. So not everything's a mechanical problem, not everything's a software problem, not everything's an electrical problem, and sometimes you need to approach it from a different avenue. And there's a lot of thought put into the small details about where to mount all the cameras and where to mount the individual sensors that are going to make the process the most reliable and the fastest possible. I'm like, we actually have 4 sensors that detect the position of the coral as it passes through the robot. And all of that thought for making the programmers' lives easier happens during the mechanical design of the robot up front. And sometimes you have to go back and move a sensor or move whatever, and that's fine. And you just have to make the best decision to solve the problem that you're trying to solve, taking the personalities and the egos out of it. So sometimes programmers like to solve things with programming problems when moving a sensor over 2.5 inches is really the right way to do it. So take the egos out of it, take the personalities out of it, and just figure out what the best way to solve the problem is. Yes.
So when you're like, let's say you're going from the reef to the feeder station, are you just doing one drive to point, or are you doing multiple along the way?
This year it was 2. There was one general, like, go to 5 feet away from it, and then the second one was auto track to pick up the piece. So.
And then you mentioned how you have a tolerance, like 2 foot of allowance to get somewhere. Is that in the drive to point? You're setting the tolerance?
Yeah. So our drive to point function, it takes in a pose that is where we want it to be. It takes in a velocity, which is how fast we're going to let the robot drive there. It takes in a rotational velocity, which is how quick we're going to allow the robot to spin while it's on the way to this point. And it takes in a tolerance, which is how close to that point we want to be before that function returns true. And it's a Boolean function that just returns true or false. And it commands the robot. It calculates the distance, angle to the robot, feeds it to the the field-centric robot controller that turns the sword modules to get us there. More questions? How are we doing time-wise?
Awful. We have 2 minutes.
Okay. Is there anything left?
There's one more slide, and it's really briefly on logging. So we don't use any fancy logging. I think Advantage Scope is a big one, but we don't log anything to a file. What we do is we record our driver station as the match is happening. And this lets us go back and look at everything from the cameras to certain sensor values. And you can kind of see that maybe here.
Is this playing?
Nope.
You got to click it, I think.
Either way, you can
Yeah, there we go.
there we go. So you can see off to the right, we have the cameras, and then you can't see the values, but all those little boxes are values.
So the other cool thing is this actually records the driver station mic.
Oh, goodness
So you can hear
gracious.
the drivers and coach communicating with each other in match. So like if something's like going wrong with the robot, you can hear the verbal communication about how they're trying to troubleshoot the problem. And it's got all the sensor values and the camera feed and the audio. And this takes us like 2 minutes to set up at the start of the year. We just like install OBS, record the screen, and that's it. So we do this because it's super easy and it's kind of cool to watch back afterwards.
It's quite fun to watch back, especially when you sync it up with the match video.
Yeah, if you overlay the two, like the full field view and this, and you can hear what's going on behind the glass, and everyone's like, "Ah, it's crazy! What's going on?" It's really fun. And if like something goes goofy with the strategy, you can go back and see like how the decisions are made in real time. Not to place blame, but just to improve going forward. And yeah, that's a big thing. Yes, question in the back. I would love to know how to do that, but we have it mapped to a hotkey. So when the announcer goes 3, 2, 1, go, he just reaches forward and hits it. Yeah.
We could probably make that. Yeah.
More questions? Yes.
Do you have a process to train the new person coming for programming? Like, do you have like a list of exercises or videos or?
No, I wish we did more stuff in the off
We
season.
have some training modules these days.
Yeah, we do have some. Most of it is trial by fire, kind of along the way.
This is true.
Um,
This is something we're trying to improve,
yeah.
but it is trial by fire.
Yeah.
If you get kids that show up and want to do this, so they're kind of okay with maybe not having structured, training programs, and instead they kind of want to sit there and look at the code and have you explain it and all that stuff. So
Looking through previous robot programs, looking through other teams' robot programs is really valuable. But there's really no substitute for programming a robot yourself. So there's only so much like training you can do off board that's going to prepare students to program FRC robots. The best way to train students to program FRC robots is to program FRC robots. So you kind of do it on the fly, and over the course of their high school career, they will get quite good at it. More questions? Yes.
Do you ever do auto and driver practice at the same time, or the two robots never up and running?
Sometimes, but not super often. No. Usually the driver practice happens like at lunch or immediately after school before mentors get here. And then if there's something specific that we're working on for auto practice, we'll just shove the practice robot over to the side and bring the comp robot out. We do all the auto development on the competition robot, just in case there's any like minor mechanical differences from one to the other, that all of our auto development is with the competition robot. After the competition robot is actually running. It lags behind that one by a couple of weeks. Yeah. And then the first time you fire the competition robot up and you fire it and everything works great, everyone cheers.
We do driver development on the practice robot.
Yes.
Do you run any auto on the practice bot?
Oh yeah. They generally work just fine. Just there'll be some weird little mechanical difference between the two of them. Like not that gripper, but the original gripper that robot had on it, like mechanically the holes were like drilled a little bit off, so the gripper was like a little bit askew. So this is really cheesy workaround. We just took the crosshairs for the camera and like moved them over to account for it. But there are sometimes some small mechanical differences. Yes.
Do you like compensate for like keep it running throughout the season? Like you make a change to a competition by moving your sensor like an inch to the left on that. Would you come back and make the change on that?
Usually we would make it on that one first.
But if it was like at a competition, then you come back.
We generally don't make any changes at competition. Like when we get there, we're ready to play, and that's like We'll put a battery in, do our checks, go out and play, come back, sit down, have a Gatorade, go play the next match. Yes. Very, very small changes. It'll be like move a point 2 inches to make an approach better, or
Yeah.
increase the timer by 50 milliseconds.
Yeah.
It's very, very small tweaks to account for unique things on the field. Yes.
Do you make that call like the first time it fails, and you do it another match, and then you actually want to go change the code versus maybe something else is a problem that's not the point exactly?
That depends what it is, and what the failure mode was. If it's like off by a mile and we know it's off by a mile and we can go back and watch the driver's station footage and go, yeah, this is off, then we'll move it. If it's something that's intermittent or not repeatable, then we may watch it a couple of times and see if it develops a pattern of behavior that we can then address. So it depends.
Okay, we have to be done,
We have to be done.
I think.
Okay, thank you very much. You've been a wonderful audience. If you have questions,